Good morning, everybody. We are here to talk about light and what light can tell us about the cosmos. If you have taken physics in your high school career, this will be a review for you. Otherwise, the last time you've seen this is either chemistry class or eighth grade. Eighth grade science. So it's been a while, so it's always good to have a little bit of a refresher and a review before we launch into um, how astronomers would use light. So where we're headed is that today in this particular presentation, this screencast is just going to cover the electromagnetic spectrum and just general properties of light. Next time we'll look at spectroscopy, and then the last piece of the puzzle will be the Doppler effect and why that's important in astronomy and what it is and how we can learn from it. Right, so here is a diagram of the electromagnetic spectrum. They call it electromagnetic because this little bundle of energy that we call light has both electric and magnetic properties, and they are entwined with one another. So therefore, we have electromagnetic spectrum. We are very, very familiar with the visible light spectrum, which makes up a very, very small portion of all of the different types of light that are mostly invisible to us. Over here on the left-hand side, you have very, very small wavelengths, very, very high frequencies, very high energy, gamma rays, and then over here so I said left, this is the right, you have very long wavelength, low frequency radio waves, and everything in between. So here, okay. Properties of light, just general properties. Light, physics, you can actually have two different models for light. One is the photon model, where light is little bundles of particles being shot out and received and given. That's the particle model, but we're going to be working with the wave model. That light and electromagnetic radiation is in waves. And waves helps us quantify it, helps us learn more about it. So we're going to stick with waves. The Greek letter lambda, kind of looks like a stick figure giraffe, is what we use to represent wavelength, or the distance between crest to crest, or trough to trough, midpoint to midpoint. Frequency is the number of cycles passed in a given time frame. So if you picture yourself, sitting on a dock and watching waves come in, and you start your timer, your stopwatch, and you want to know how many waves pass by your feet every minute, you are calculating frequency. So generally, the trends are the shorter the wavelength, the higher the frequency. The longer the wavelength, the lower the frequency. Since light is pretty much traveling at the same speed regardless of wavelength, usually the shorter the wavelength, the higher the energy of the wave, which is why gamma rays, being the shortest wavelength, has packed so much energy in a gamma rays, which is why they're bad for your cells. Other properties of light, the speed of light, represented by lowercase c, as in Einstein's famous E equals mc squared equation, is 300 million meters per second in a vacuum. That is the fastest thing that we know of. A light year, therefore, is the distance that light can travel in one Earth year, shot out at 300 million meters per second. A light year ends up being around 9.5 or almost 10 trillion kilometers is a light year. And that's even hard for our brains to even fathom that type of distance, but that's incredibly far. There are distances that astronomers use that are even farther than that. A parsec is 3.26 light years, and that is how far away, why that seems random. A parsec is how far away from Earth you need to be, where you can see Earth and the Sun, that one astronomical unit, that distance, equal to 1 arc second, or 1/3600th, 3600th, yes, of a degree. I doubted myself in how I said that. So that's what a parsec is. For you Star Wars fans, or at least the New Hope, they mistakenly said that Han Solo did the kettle run in X number of parsecs. Parsec is not a unit of time, it's actually a unit of distance. So being Earthlings, our eyes have evolved to differentiate really well between wavelengths of 400 and 700 nanometers. Nanometer is a billionth of a meter. That is the range of visible light. Everything from red, orange, yellow, green, blue, indigo, violet, and all of the millions of shades in between. White light, or sunlight, that's coming from our star is all of those colors combined. You can refract it or bend it through a prism or a piece of glass or water, and turn them back into all of their individual colors, and that's how we make rainbows. Remember that an object that is a certain color that you see, let's say, as red, an apple, that apple's skin is absorbing all of the other wavelengths except red. And red is reflected back to your eyes, and your eyes tell your brain that that is red. Earth's atmosphere is very good at scattering blue light, but absorbing all the other wavelengths. Therefore, daytime sky is blue. Astronomers use telescopes to see things and to use light. In fact, as long as if you don't have a meteorite to study in a laboratory or a moon rock, pretty much astronomers, the only thing that they have in their arsenal is light. That's the only direct measurements that they can make. So light is incredibly important to astronomers because in many cases it's the only thing they have. If you have a telescope at home, it's most likely an optical telescope, meaning that it's seeing just visible light. Roy G. Biv. Right, and here's in the upper right, here's the Crab Nebula as optical telescope. But we now have the technology that we can make telescopes that see in different flavors of light. So we have radio telescopes, we have ultraviolet telescopes, we have X-ray telescopes. And now astronomers can look at that same Crab Nebula through different lenses and learn more about that nebula, or a galaxy, or a planet, or a moon, or whatever it might be. So I'm going to just take us through, a little bit of a scavenger hunt through our electromagnetic spectrum, all the different flavors, just give you a taste of what they do and how astronomers use them. So we'll start with the very, very high energy. So high frequency, very, very short wavelength light. These are gamma rays and X-rays, where their wavelengths are less than 1 nanometer. Earth's atmosphere and magnetic shield protects life, thank goodness. So we actually need to make space telescopes to be able to see in gamma rays and X-rays, because thankful to Earth's atmosphere and our magnetic field that these horrible damaging radiation waves are not entering Earth's surface. That's a good thing. But we do need to send out space telescopes in order to see in that. So where are these things coming from? Supernova, so when stars explode, and stars generally, when they're fusing hydrogen into helium or fusing heavier elements, they are releasing gamma rays and X-rays, even our own sun. A black hole in a binary pair has been known to give off X-rays. They call it an X-ray binary. And there's also gamma ray bursts. I put a big question mark there because astronomers really don't know where or why these random bursts of really high intensity energy is coming from other places in the galaxy. So I love it when we have to put a question mark because we don't really know. As we get a little bit less intense, ultraviolet light is between 1 nanometer and 400 nanometers. Stars, especially younger stars, like our sun is kind of middle age in its adult life, but our sun gives off ultraviolet. A lot of stars, actually pretty much all stars, give off ultraviolet light. Most UV gets absorbed by Earth's atmosphere, especially ozone, but not all of it. That's why you get sunburn, and that sunburn is because your skin has experienced a little bit too much ultraviolet. Both gamma rays, X-rays, ultraviolet, these high energy light waves have been proven to shred DNA. And since you've all taken biology, you know how important DNA is and replicating DNA. So therefore, exposing yourself to these things will not turn you into the Hulk. It'll probably give you skin cancer or some other sort of cancer. Right? That's why when you go get X-rays, either at the dentist or at the doctor's office, they put a lead vest over your vital organs so that they don't experience, the DNA shredding effect of high energy light waves. We'll skip over visible light because we'll spend plenty of time with that. Infrared, it's what we know as heat. Dust, gas clouds, organic molecules all have residual heat that we can detect. They might be too cool to emit any visible light. Only things that emit visible light are things that are hot enough to like fuse hydrogen, or get really, really hot that it makes its own light, but we can still use infrared telescopes to find things. There is a lot of interference with Earthlings. Like we give off heat, our bodies give off heat, we are warm-blooded, all of our machines give off heat. So you have to use high altitude telescopes, even special planes, and I'll show you a picture in a second, that can orbit almost in the stratosphere to get above the bulk of Earth's atmosphere in order to get infrared readings. Microwave and radio waves, they are incredibly important in the 21st century. This is what all of our Wi-Fi and radio and television signals go through. They are of the longest wavelengths. Microwaves actually helped provide evidence for the Big Bang. We'll talk more about it at a later time. People who are searching for extraterrestrial intelligence are using radio waves because they thought, well, if humans communicate via radio waves, probably other intelligent beings in the galaxy would also communicate through radio waves. Solar activity can be measured in radio waves and microwaves, and the surfaces of planets can give off radio waves. Cool. Here is a picture of the Orion Nebula. It's right below Orion's belt. On the right, you'll see a visible light photograph, but on the left, you will see an infrared image taken in infrared light. So you can see way more dust and gas than you could see in the visible light because you're using infrared. Other cool ways and methods and technology that we use to measure light. The top left is the James Webb Space Telescope. Sadly, it's still on Earth's surface, and it's been, waiting to be launched for probably the past decade. There's always something that comes up, either a budget shortfall or engineers that need to make something new. They're making up new technologies on the spot just to get this James Webb Space Telescope out the door and into Earth's orbit. It is still sadly on the ground, but it's supposed to be like the Hubble Space Telescope 2.0 and be able to do way more than our Hubble Space Telescope could do. On the top right photograph is the Very Large Array in New Mexico. If you've seen the movie Contact with Jodie Foster, that is where she is, using all of those radio telescopes. Notice that the radio telescopes look like a satellite dish because it's essentially the same thing. They are all lined up and interconnected to be able to see into a huge chunk of space and look for signs of other beings trying to communicate. Bottom right is an airplane. It's a NASA plane, and out the fuselage, that is the SOFIA infrared telescope. So they have to get that plane higher than 30,000 feet, almost up into the stratosphere, in order to use it and be able to not have that interference. And we do have the Chandra X-ray Observatory. It is orbiting Earth at about 1 million miles. That's how we see in X-rays, because that is free from the interference of Earth. These PBS crash courses are really great. I'm not going to do it here in the screencast, but watching through about 4 minutes and 50 seconds, the first 4 minutes and 50 is definitely a good recap of everything I just talked about. And that is all. So I hope you enjoyed this screencast, and take care.